Of all the spacecraft to have visited other worlds, there are two which have travelled further than any other, revealing more to us about our solar system than their inventors ever could have imagined. They are the legendary pair of Voyager probes. Marvels in human engineering and ingenuity, and still the only spacecraft ever to have visited the ice giant planets, Uranus and Neptune. The story of their almost half a century in space is among the grandest of them all, and it makes up the topic of our video today, in the final chapter on this trilogy of probes that explored the planets. What started out as an opportunistic attempt to reach the ice worlds rapidly ballooned into a voyage beyond the solar system itself, into the cold, lonely depths of the space between stars. In the early space age, it was noted by Jet Propulsion Laboratory physicist Gary Flandro that a rare planetary alignment event involving each of the four giants was due to take place late in the following decade. Occurring only once every 175 years, this promised a generational opportunity to visit each of the worlds in the outer solar system from Jupiter to Pluto, cutting down considerably on distance, journey time, and fuel requirements. By 1966, the JPL had drawn up plans for an ambitious project known as the Planetary Grand Tour, constituting 4 distinct probes, each making use of this alignment to visit 3 of the 5 contemporary outer planets. And by 1969, NASA had established a working group for the Grand Tour's development. But moving into the following decade, the programme came under increased financial scrutiny. Its extravagant specification quickly ran up estimated costs of more than $1 billion, at a time when Congress was more interested in allocating funding for the upcoming Space Shuttle programme. As such, the Grand Tour was axed in 1971 to be replaced by a more modest, scaled-back mission as part of the Reanimatd, whose resoundingly successful spacecraft designs were currently enabling the exploration of Mars and Venus. But these probes, then designated Mariner Models 11 and 12, would be pitched for funding solely as a gas giant mission to visit Jupiter and Saturn, so as not to incur the high costs on paper associated with going any further. But they would both be launched on trajectories which left the door open for optional, additional voyages that would achieve most of the Grand Tour's objectives if the primary mission's aims were fulfilled. Mariner 11's trajectory, designated JST, would take it by Jupiter and then onwards towards Saturn, before culminating in a flyby of the latter's largest moon, Titan, a high-priority unexplored target for astronomers back then. Mariner 12's path, meanwhile, designated JSX, would repeat these same steps as it swung by the gas giants, but could then be directed on towards Uranus if its predecessor's Titan mission was successful. If not, then Mariner 12 would have to forfeit its journey to the ice giants in favour of another attempt at a flyby of Titan, leaving only the possibility of carrying on to Pluto thereafter. And in any case, both probes would then be directed on paths taking them out of the solar system altogether, for an exciting, extended trip to study interstellar space. Both spacecraft were fitted with 11 core instruments, including visible and radio probing cameras, infrared and ultraviolet spectrometers, plasma probes, particle surveyors, and magnetometers for sampling the gas giant's magnetic fields. But by the time these probes materialized, their technology had progressed well beyond their Mariner bases. And thus, only a few months before their 1977 launch, NASA held a vote to rename this expedition, eventually settling on the Voyager program. These probes, Voyager 1 and Voyager 2, have defined an entire generation of astrophysics, their names immortalized in the scientific world. They have gone further and seen more than any other spacecraft, delivering unparalleled insights into even the most basic of astronomical phenomena. Both probes were launched from Cape Canaveral late in the summer of 1977. Despite their designations, it was Voyager 2 that lifted off first, giving it a head start on its longer and slower stopping service route, calling at each of the 4 large planets. Almost straight away, however, its ice giant mission was thrown into jeopardy, with the turbulent and almost failed launch of its twin spacecraft a few weeks later on September the 5th. But after recovering from its stuttering start, Voyager 1 set out on its express route to leave the solar system via the gas giants, and overtook its counterpart from inside the asteroid belt in mid-December of that same year. Voyager 1 would exit this belt around a year later, before coming within range of the Jupiter system and initiating its observation sequence in the following January. Its instruments studied the Godfather planet for around 4 months, snapping over 19,000 images in a variety of wavelengths, though its most tantalizing findings came within the days of its closest approach, on the 5th of March 1979. It studied the gas giant's clouds and shed new light on the nature of its great red spot, and even discovered a thin, faint extended ring system surrounding the planet. But its most unexpected revelations came from the Jovian moons, especially around Io, where Voyager saw the outline of an active volcanic eruption rising from its surface. This was the first time that any kind of active volcanism had been seen on a body other than the Earth, with its ejecta falling into orbit along Jupiter's magnetosphere, feeding its plasma torus. Elsewhere in the system, Voyager revealed Europa to be a cold, smooth and craterless moon with an icy surface, in stark contrast from its hellish sibling. It also made the first detailed maps of the surfaces of Ganymede and Callisto, Jupiter's 2 largest moons, revealing them both to have older, less active surfaces battered by bombardments for billions of years on end. Upon starting its exit from the Jupiter system, Voyager 1 wrapped around the Godfather planet and received a gravitational assist which catalyzed the craft's speed, catapulting it onwards for a further 18 months towards its next target, the solar system's crown jewel, Saturn. In late August 1980, Voyager 1 commenced with its Saturn observations phase, and made its closest approach in mid-November, coming within 124,000 kilometers of its clouds. As it intersected the gas giant's ring plane, its cameras saw complex, gravitationally bound structures forming within, providing fascinating new insights into the physics and dynamics of planetary ring systems. It measured a day on the gas giant as just 10 hours and 39 minutes, and even saw complex, aurora-like emissions emanating from within its polar regions. It then began with the most critical phase of its mission, with potentially drastic ramifications on the future of human spacefaring, the make-or-break flyby of Saturn's unique large moon, Titan. It had long been known to scientists that Titan possesses a substantial, gaseous atmosphere unlike any other moon in the solar system. And after the images snapped by Pioneer 11 teased just how thick and dense, a flyby of Titan raced up the rungs of NASA's priorities. Therefore, Voyager 1's principal objective was to probe this atmosphere in depth for the first time. And if it had failed, Voyager 2's trajectory would have been rerouted round Titan for a second attempt, forfeiting any possibility of visiting Uranus or Neptune. Even today, Voyager 2 is still the only probe to have reached the ice giants, and so you can imagine how much was riding on the predecessor's Titan flyby preceding the wreck. On November the 12th, 1980, Voyager 1 came within just 4,000 kilometers of Titan's clouds, before passing behind the moon relative to the Earth to observe the effects of sunlight and radio signal occultation on its layers of haze. The effect of these signals was then used to infer the atmosphere's temperature, pressure, and chemical composition, delivering the first detailed insights on this potentially habitable mode of the outer solar system. Thereafter, Voyager 1's Titan leg was complete, and upon snapping some images of Saturn's other moons, its planetary science mission was concluded. The probe then arced under the gas giant's south pole and received a gravitational slingshot which sent it barreling upwards away from the Sun's ecliptic plane. Having been accelerated by assists from both gas giants, Voyager 1 had now been set on an unstoppable charge to find the edge of the solar system, searching for the boundary of interstellar space. But another 20 years would pass before the probe began to even scratch the surface of the space between stars. In the meantime, many of its instruments would be powered down to conserve energy for its longest ride. It maintained this slumbering outwardly passage for around another decade, before its cameras stirred once more to capture one final glimpse of the planetary neighbourhood. On Valentine's Day 1990, Voyager 1 turned back towards the Sun to snap our solar system's family portrait, a top-down mosaic of the Sun and its satellites, capturing 6 of the solar system's planets from a single point of view, the most distant ever observed. Among the several dozen images it contains is one of the most iconic photographs of all time, the pale blue dot. This grainy, low-resolution image shows our entire world from over 40 astronomical units distant, rendering it nothing more than a tiny, barely distinguishable speck, containing every inch of the human tapestry woven into one profound glimpse. Every single atom, cell, animal, and person. Every civilization, religion, culture, and conflict. Every human's joys, dreams, worries, and fears. All of it crammed into this tiny, pinpricked dot of light suspended in a sunbeam. After this, Voyager 1's cameras were powered down for the final time, as the probe would devote all its remaining resources to feeling its way towards interstellar space. Voyager 1's image was snapped only a few months after the conclusion of its successor's planetary mission. As we mentioned, although it's lifted off a few weeks before, Voyager 2 proceeded more slowly towards its gas giant stop-offs, and would encounter the Godfather planet around 4 months after its predecessor. In early July 1979, Voyager 2 spent 4 days up close with Jupiter, resampling and reaffirming the data gathered by its twin, independently verifying volcanic eruptions on Io, and compiling even sharper mosaics of the other Galilean moons. It also observed a number of transient weather events in Jupiter's torrid upper atmosphere, before angling around the planet to receive a gravitational boost. It then set out on the long road to Saturn, encountering the system in late August 1981. Its closest approach came on the 26th, where it once again passed behind the planet's atmosphere to perform occultation experiments probing its chemical characteristics. It measured Saturn's temperature, estimated its internal pressure, and observed a variety of weather phenomena in its clouds. It also made further measurements of Titan's atmosphere, albeit at a higher distance, along with images of Saturn's other large moons, like Enceladus, Tethys, and Iapetus. It also studied the giant's shimmering ring plane, and passed through its bounds to receive another gravitational boost. Despite a minor wobble when the spacecraft's scan platform malfunctioned unexpectedly, its engineers were able to rectify this fault, and Voyager 2 was cleared to embark on the next phase of its journey, the long-awaited lonely passage into ice giant territory. The ice giant Uranus and Neptune are noticeably departed from their step-sibling gas giants. With smaller statures and smoother surfaces, and higher fractions of volatile substances, these worlds do not bear the same bedazzling features boasted by Jupiter and Saturn. Uranus, in particular, has a near featureless surface which shrouds it in intrigue. Its counterpart Neptune, on the other hand, is characterized by a broad range of extreme weather, with storm clouds and cyclones emulating those on Jupiter, along with a peculiar subsystem of surrounding satellites. Both of these worlds lie considerably farther from the Sun than the gas giants. A distance of almost 1.5 billion kilometers separates Saturn from Uranus, while an even greater expanse divides the ice giants. As such, even with the gravitational boosts received from both gas giants, Voyager 2 would 5 years before encountering its first target within the fringe of the planetary neighbourhood. On the 24th of January 1986, Voyager 2 became the first and still only probe to visit Uranus, when it made its closest approach of about 81,000 kilometers from its outer edge. While it found most of the planet obscured by detail diminishing haze, contrast-enhanced false color images started to peel back its layers and unravel its mysteries, revealing bands of concentric clouds swirling around the planet, glowing in ultraviolet light. The probe measured a day on the ice giant as 17 hours and 14 minutes, as it spins at an almost perpendicular angle, misaligned with the plane of its orbit by almost 98 degrees. Uranus is the only planet in the solar system which spins in this manner, and scientists now believe it to be a direct result of a giant impact, which tipped the planet over and rolled it on its side more than 4 billion years ago. One of Voyager 2's most surprising revelations was that, much like its rotational axis, Uranus's magnetic field is also inverted at the same angle, suggesting an icy impactor once crashed into the giant and flooded its interior with shards of frictionally heated, shattered volatiles. The probe also identified signs of other impacts in the Uranian system, when it made high-resolution maps of a number of its largest moons, uncovering complex fault lines on Miranda, similarly thought to owe to past large impacts. The spacecraft also discovered no less than 11 previously unseen moons of Uranus, including its pair of shepherd moons, Cordelia and Ophelia, which exert counterbalancing gravitational influences that tend the material in the giant's vertical planetary ring system. And the dataset for Uranus captured by Voyager 2 is still being combed and interpreted to this day. Only as recently as 2020 did scientists spot new evidence for a magnetic bubble surrounding the giant, known as a plasmoid, after reprocessing the Voyager data. A true testament to the profound reservoir of knowledge assembled by this spacecraft, which even 4 decades on refuses to run dry. Upon departing the Uranus system, Voyager 2 received yet another gravitational boost, which steadied its course for a further 2.5 years, en route to its final planetary target, Neptune. In mid-year 1989, Voyager 2 began honing in on the Neptunian system, compiling a collection of more than 10,000 images of the last unexplored contemporary planet and surrounding environment. It uncovered an apparent dark spot aggregation of storm clouds reminiscent of the Great Red Spot, but one which has vanished in the decades since. It also found Neptune to have its own thin, tenuous ring system of material, meaning all 4 of the giant planets host one to wildly differing degrees. It made its closest approach to the ice giant on the 25th of August 1989, taking it barely 5,000 kilometers above the planet's north pole. This path was chosen to enable a flyby of Neptune's largest, most perplexing moon, Triton, the only substantial satellite in the solar system in a retrograde orbit around its parent. As such, Triton is not believed to be a natural, co-accreting moon of Neptune. In fact, it is thought to have started its journey as a Pluto analogue, a frozen volatile dwarf planet which was eventually captured in orbit by the ice giant. About 5 hours after its Neptune encounter, Voyager 2 flew by this adopted moon from a distance of about 40,000 kilometers, snapping stunningly detailed mosaics of its frosty, frozen terrain. These images revealed jaw-dropping levels of surface activity, the likes of which we never expected to find on a moon so far from the sun, including evidence of cryovolcanism, nitrogen geyser eruptions, and even a thin, tenuous atmosphere of its own. In addition, Voyager 2 pinpointed 6 new Neptunian moons and photographed their paltry surfaces for the first time. It then wrapped around the planet en route to its south pole, receiving one last gravitational assist that sent it hurtling downwards to the south of the Sun's ecliptic plane, where it would embark on its own interstellar voyage. And with that, the exploration of the solar system's current planetary contingent was retroactively completed. In just 25 years, NASA had gone from barely breaching the bounds of interplanetary space to arriving first at all 8 modern planets. And their grand tour of the outer solar system had largely been completed. Only one final destination remained: the space between stars. And in the decades since, both Voyager probes have maintained unwavering, outwardly trajectories to exit the solar system, searching for drop-offs in the prevalence of the Sun's solar wind emissions, signalling the beginning of the end of its territory. Solar wind is the consistent outflow of charged particles emitted by the Sun's inner atmosphere. This ejector streams out into space in all directions, expanding several times farther than the scale of the planetary neighbourhood. This results in a much larger, more diffused plasma atmosphere which partitions the Sun's domain from the rest of the galaxy, known as the heliosphere. The heliosphere encompasses the Sun's magnetosphere, astrosphere, and the extent of the solar wind. But this is not a spherical bubble, and is instead more like the coma of a travelling comet, a windsock trail of solar emissions, carving the Sun's place within the interstellar medium, the intersecting clouds of stray plasma lacing the gaps between stars. And so, the final objective of the Voyager probes would be to feel their way through space with their remaining instruments, searching for the boundary where the Sun's emissions start to nullify, in what we can truly call interstellar space. Exiting the heliosphere to reach this stellar no man's land starts with the termination shock, the point at which the Sun's solar wind abruptly starts to slow down as it feels the pressure of interstellar radiation. These supersonic emissions tumble from speeds in excess of 500 kilometers per second to less than 100 kilometers per second, yielding a shockwave-like rim which marks the innermost edge of the heliosphere, analogous to the innermost edge of a water flow as it splashes against a basin. It's not entirely clear when Voyager 1 passed into this zone, as its solar wind detector had been powered down by the time it arrived, but it is thought to have been around December 2004, when the probe was 94 astronomical units deep. Beyond this point, the Sun's emissions become increasingly suppressed by the oncoming interstellar medium, compressing the solar wind into a hot, dense wall of slow-streaming plasma, known as the heliosheath, which Voyager 1 plunged into in 2005. As this wall presses against the flow of interstellar space, its velocity continues to plummet until it finds balance with the strength of the galactic medium and grinds to a halt. This marks the outermost boundary of the heliosphere, known as the heliopause, and beyond it, the Sun's emissions start to be repelled as non-solar radiation prevails. Voyager 1 passed through this region sometime in mid-year 2012, and while its solar wind detector was unable to let us know, the craft's charged particle instrument recorded a marked 9% uptick in bombardment from intergalactic cosmic rays. This, coupled with the first detection of Lyman alpha radiation from the Milky Way, removed all doubt that Voyager 1 had become the first man-made object to exit the Sun's territory and reach interstellar space. In August 2012, at a distance of more than 121 astronomical units. It would be joined in the abyss around 6 years later by Voyager 2, which would pass beyond the heliopause in November 2018, at a depth of around 100 astronomical units, a whole Neptune's distance closer than its predecessor, as the southern side of the heliosphere is more compressed by magnetic fields. As of the making of this video, at the turn of 2024, Voyager 1 is around 160 astronomical units from the Sun, barely cropping up on the Deep Space Network for the occasional call home, from almost 25 billion kilometers. But by 2025, it will lack the power to operate even one of its remaining instruments, and the probe will fall radio silent. Voyager 2, meanwhile, currently around 135 astronomical units deep, should stay in touch until the mid-2030s. But both probes will be defunct long before they reach the actual edge of the solar system. In around 300 years, Voyager 1 will approach the start of the hypothetical Oort cloud, a postulated reservoir of long-period comets arriving from wide angles. These comets are thought to loosely follow the Sun in a large, diffuse extent of bubble stretching far beyond the Earth's for over a light year into space and back. It will take further 30,000 years before Voyager passes out to the other side. But once it is clear, the solar system will be in the rearview mirror, and the probe will continue onwards as it passes by other stars. After a further 10,000 years of travelling, Voyager 1 will pass within 1.6 light years of the Camelopardalis constellation member Gliese 445. And if it stays this course undisturbed for another 3,000 years, it will come within less than 1 light year of the Cygnus member TYC 33551. Hopefully by then, it will afford a better name. Voyager 2, on the other hand, will pass by the 10-light-year distant star Ross 248 in around 42,000 years, before coming within 4 light years of the Sirius group in 300,000 years. Thereafter, their paths become harder to predict, as both probes will latch onto the galactic core of the Milky Way, drawn into its time like a crater in a cosmic carousel. But they will persist on this journey for hundreds of millions of years to come, and who knows what else they might pass by during their longest ride. Perhaps they will wander into systems hosting intelligent life on their own. With this in mind, and much like the Pioneer probes, both Voyagers are equipped with a signature for humanity, specifically a pair of golden records designed to be claimed by an alien species. Like vinyl records on Earth, the golden records can be played using the apparatus attached to convey a broad range of sounds, greetings, messages, and even images of our planet and the human experience. Atop each cover are instructions inscribed for making it work, including depictions of the record configured in the correct position, with time codes and signal frequency indicators for achieving the correct rotation. There are also guiding units, such as the hyperfine transition of hydrogen, and the same pulsar map that featured on the Pioneer maps, for triangulating the position of Earth based on 14 nearby neutron stars. In addition, both records are coated in uranium an isotope which rated decay can be used to infer the time elapsed since it was plated. And so, even if something intelligent happened to recover, they should still be able to achieve some useful information from the probe at the very least. Whether there exists a civilization advanced enough to locate a defunct, radio-silent probe from potentially light years beyond their system is another question entirely. Only 5 spacecraft have ever reached the escape velocity needed to leave the solar system, overcoming the gravity of the Sun for the duration of the journey beyond. They are Pioneer 10 and Pioneer 11, Voyagers 1 and 2, and finally, New Horizons, one of the flagship missions of the 2010s, which fulfilled the final objective of the original Grand Tour: to visit the solar system's dwarf planet, Pluto. Up until 2006, and thus throughout the duration of the Voyager planetary mission, Pluto was seen as the solar system's 9th planet, but the chance to reach it had been passed up in favour of studying Titan, leaving a glaring omission in NASA's planetary set. Therefore, only shortly after the conclusion of Voyager 2's Neptune encounter, plans for a Pluto mission started to be drawn up, though it would take another decade before one actually materialised. But moving into the new millennium, a project nicknamed New Horizons was soon selected for development by NASA, but initially failed to win the backing of the then lead administrator, Sean O'Keefe. Eventually, however, after a long campaign of public support and lobbying by NASA administrators, a report conducted by the US's National Research Council in 2002 placed New Horizons at the top of its wish list, even ahead of missions to Jupiter and the Moon. This mission would be allocated as the maiden voyage of NASA's New Frontiers program, an initiative for so-called medium-range missions which could deliver high scientific returns without incurring significantly complex or expensive developmental challenges. Its team consisted mostly of scientists from former Pluto-bound initiatives, such as the Pluto Kuiper Express, which, in addition to studying the then 9th planet, would also have visited another object within the Kuiper belt, the vast circumstellar disk frosting the edge of the solar neighbourhood, where most of the system's dwarf planets can be found. As such, after carrying out extensive analyses of the 9th planet and its moon Charon, New Horizons would visit at least one other Kuiper belt object to sample a range of materials lurking within its bounds. The spacecraft lifted off from Cape Canaveral on the 19th of January 2006, only shortly before Pluto was downgraded to dwarf planet status by the International Astronomical Union. But its mission objectives remained unaltered as the probe pressed determinedly onwards towards the now honorary 9th planet, falling only at Jupiter along the way for a gravitational boost. It spent much of its 9 years en route in hibernation, as it crossed the orbit of Saturn in 2008 and then Uranus in 2011. On the 25th of August 2014, exactly 25 years after Voyager 2 encountered the system, New Horizons crossed the orbit of Neptune, reviving its instruments for its observations phase some 5 months before its closest approach. Almost immediately, it spotted a pair of tiny fragmental moons lurking around the dwarf planet, adding to the two discovered by the Hubble telescope in 2005. On the 14th of July 2015, New Horizons made its closest approach to Pluto, flying just 12,500 kilometers from its surface. In doing so, it captured a stunning flyover sequence of the dwarf planet's frosty nitrogen landscape, intersected by ridges of water ice mountains and dotted with large impact craters. It revealed a long-speculated bright patch on the surface of the dwarf planet to be a gigantic, 1,000-kilometre stretching sheet of frozen volatiles, lying atop a colossal impact basin carved into its landscape. Further down, it uncovered multiple, overlapping lines of evidence for a tidally heated, liquid water ocean, like the ones found on Europa and Enceladus, including fault lines, convection, and evidence of cryovolcanism. It then turned its gaze to Pluto's ice dwarf partner, Charon, the largest moon, or perhaps binary dwarf planet, relative to its parent in the solar system. On this perplexing Kuiper Belt object, New Horizons identified similar signs of past cryovolcanism and a long-lost liquid ocean now frozen into solid ice. and upon starting its exit from the Pluto system, New Horizons turned its cameras back for a final glimpse of the world and captured one last surprise: the sunlit outline of its sparse, puffy nitrogen atmosphere. Truly a new horizon to behold. With Pluto ticked off and the exploration of the planetary neighbourhood now inarguably complete, the spacecraft was steered towards another Kuiper Belt object, which it was decided would be the snowman-shaped planetesimal oddity Ultima Thule. Better known as Arrokoth, this composite planetesimal object presented a unique opportunity to study ancient material, preserved from the age before the planet's decay. And while it was unnoticed, the spacecraft continued to study various sites in space. In 2017, it broke the pale blue dot's 27-year record of the most distant photograph ever taken, when it snapped a calibration image of the Wishing Well cluster some 41 astronomical units from Earth. And on New Year's Day 2019, at a distance of more than 43 astronomical units, New Horizons encountered Arrokoth and studied this festive cosmic snowman, mapping its 3D surface topography while also searching for signs of rings, dust, comas, and satellites. It determined the object to be the product of two planetesimals sticking together, and found its redness likely the result of bolins, organic molecules also found on Pluto and Titan. Since then, the probe's uses have ranged from snapping more distant shots of other Kuiper Belt objects to studying our nearest non-solar neighbour, Proxima Centauri. And right now, at the end of 2023, the probe is around 58 astronomical units from Earth, with all its major instruments still fully operational. And long before its cameras are powered down, it will be used to snap another family portrait picture of the solar system, only this time one which contains Pluto as our honorary planetary neighbour. But for now, its focus remains on Kuiper Belt objects, with plenty of scope to redirect the probe to fly by another planetesimal object, though a suitable target has still not been found. But once its Kuiper Belt mission is complete, New Horizons will, like the Voyager spacecraft, shoot off on a trajectory to leave the solar system entirely. And though not equipped with a golden record, the spacecraft does contain another signature of humanity, though quite a different one to say the very least. Instead of a pulsar map or astronomical assignment, New Horizons contains a sample of the ashes of Clyde Tombaugh, the man who discovered Pluto and who assisted in its research efforts all the way up until his death in 1997. Though he never quite got to see a Pluto-bound spacecraft realised, part of his being has now been closer to the world than any other piece of humanity, and his remains will continue to stream for light years beyond the solar system, barreling endlessly around the galaxy long into the distant future. I don't know about you, but ashes in a spacecraft sounds way cooler than your standard burial or cremation. And when I depart this world, I certainly know where I want my remains to go. And with that, I wish you all a very Merry Christmas, a Happy New Year, and I'll see you in 2024. Organic molecules also found on Pluto and Titan. Since then, The probe's uses have ranged from snapping more distant shots of other Kuiper Belt objects to studying our nearest non-solar neighbour, Proxima Centauri. And right now, at the end of 2023, the probe is around 58 astronomical units from Earth, with all its major instruments still fully operational. And long before its cameras are powered down, it will be used to snap another family portrait picture of the solar system, only this time one which contains Pluto as our honorary planetary neighbour. But for now, its focus remains on Kuiper Belt objects, with plenty of scope to redirect the probe to fly by another planetesimal object, though a suitable target has still not been found. But once its Kuiper Belt mission is complete, New Horizons will, like the Voyager spacecraft, shoot off on a trajectory to leave the solar